This presentation follows on naturally from the modal analysis presentation. If you haven't tried that exercise, take a step back and go through the modal analysis tutorial, then before closing it down, come back to this exercise. From a designer's point of view, even if you could argue that the basic shape of this particular part is largely determined by other factors, largely determined by the requirements of the parts surrounding this plate, there would still be one absolutely vital design consideration that would need to be decided with a high level of precision, and that's the thickness of this plate. Clearly, the plate needs to be thick enough to be strong enough, but then of course, too thick means increased costs and unnecessary weight. So how then could a designer know what's the optimum thickness for this plate? Essentially what we're going to do in this exercise is set given loads that this plate has to carry and work out what's the minimum thickness that will allow the plate still to perform. Once we've worked that out accurately, we can confidently say that we've got a part that works to 100% of capability at the minimum cost and weight. So here's the process then. Having just completed the modal analysis for this part, we can go into the browser and hover over the modal analysis node here, right click and say copy simulation. On this new copy I've made, I'm going to right click and say edit simulation properties, and up comes the edit simulation properties dialog box. In the name I'm going to call this parametric because the analysis that I'm looking at here relates entirely to the sizes. Under design objective, I'll go to the drop down and select parametric dimension, select static analysis, and OK. The next thing to do is to click on the parametric table option and then go into the browser and right click on the part and say show parameters. And up comes the select parameters dialog box, and I'm going to get a chance to select any one of the parameters that define this plate. The specific parameter that I'm interested in is the one that governs the thickness of the plate. So if I hunt down the list of all the parameters, it turns out that it's dimension D22, the 4mm thickness. So I'm going to check the box and say OK. And that dimension is entered into the parametric table here. Currently then, the thickness for this plate is 4mm, but I want to check it across a range of thicknesses, so I'm going to click on it once and edit that value to 2-6, and if I hit return, then I get :3 at the end of it, and essentially what that means in plain English is that the value for the thickness of the plate now is between 2mm and 6mm, tested 3 times. So there'll be a test at 2, 4 and 6. So that I can take a look at these 3 options, I'm going to right click on this line here and say generate all configurations. And currently the software is creating 3 plates at the 3 thicknesses. And if I use a slider, I see that the current value is 4, and I can slide up and see the same plate at a value of 6mm thick and slide all the way back to a value of 2mm thick. Keep in mind our goal here in this simulation is to come up with the lightest part that still has the appropriate strength. So I'm going to create a couple of constraints that allow me to govern that. I'm going to right click on the constraint name here and say add design constraint. And from the options I'm going to select mass and say OK. So we have a mass constraint now. I'll do the same thing again, right click in the same area and again pick add design constraint, and this time I'm going to select the von Mises stress and make sure that all geometry is selected and say OK. So between the two of these I can make sure that I have a finished result within an appropriate mass with an appropriate strength. It would be appropriate to set the maximum strength of the plate just now, so I'll go into constraint type under maximum von Mises stress and click it, and from the drop down menu say upper limit and set that upper limit at 10 megapascals with a factor of safety of 1.5. The next thing to do would be to place the plate under a realistic load. So I'll click on the force load option here, and the force dialog box is asking me to nominate the location for the load. So I'll click this face here and set the magnitude of that load at 10 newtons and say OK. One final point before we run the simulation is that we can increase the accuracy by going into the prepare area and clicking on the convergence settings and setting the maximum number of H refinements to 1. Say OK. And we're now ready to run the simulation. I'll say run. Just before we look at the results, we'll go into the Adjust Displacement Scale option, and from the drop-down menu we'll go to Actual. That will give us a more realistic looking animation when we come to it. Let's look in the parametric table just now though to see the results. So one thing we can see from the results is that we get a green circle indicating within acceptable limits for the von Mises stress value when we're set at a thickness of 4 millimeters for the plate. If we slide that down to 2 millimeters, then that value goes out of range. Essentially, in plain English, that's saying that the plate wouldn't be strong enough at 2 millimeters thick. If we slide that up to 6 millimeters thick, then it's well within the acceptable value, but we're paying a penalty for the extra weight and therefore extra cost. So the clear message here then is that 4 millimeters thick for that plate is ideal. In this way we can be absolutely sure that this plate hasn't been over-engineered. I'm going to go into the constraint type for the mass and click on it and go to the drop down menu and say minimize. And we can see from that at a value of 4 millimeters thick, then the von Mises stress value is 6.3 within acceptable limits. In other words, is strong enough. And if I slide down to 2 millimeters thick, we see that we've gone out of range now. We've got a red box here indicating essentially that the plate wouldn't be strong enough at that thickness. If we slide right back up to 6 millimeters thick, we're well within range, but we're paying a penalty here with the increased weight and therefore increased cost. So the ideal setting is 4 millimeters thick. In that way we can be sure that the plate hasn't been over-engineered.